In a plant, various pieces of equipment, such as pumps, tanks, and heat exchangers, are connected by piping in groupings called systems. Systems that contain liquids or gases are commonly referred to as fluid systems. To ensure that plant processes operate smoothly and efficiently, it's important for operators to understand how these systems function. In a plant, many different pieces of equipment work together to perform one or more jobs. Any group of connected components that function together to carry out a specific task can be referred to as a plant system. For example, this steam generating system provides the steam that's used by this plant. Like most systems, the steam generating system is made up of several smaller systems or subsystems. For example, it has a fuel subsystem to supply fuel to a boiler, a steam distribution subsystem to transport steam from the boiler to plant equipment, and an instrumentation and control subsystem to monitor and control operating conditions. Many plant systems are fluid systems. By definition, a fluid is anything that flows, but in general, fluids are liquids and gases. For example, the water in this discharge channel is a fluid, as is the flue gas flowing from this stack. Slurries, which consist of solids mixed in liquids, can also be classified as fluids. The operation of a fluid system can be affected by different factors. One of the most important of these factors is pressure. One form of pressure is illustrated in this simplified fluid system. Here, a non-moving or static liquid, in this case water, exerts pressure on a gauge mounted near the bottom of a container. The pressure exerted by a static liquid is known as hydrostatic pressure, and it's related to the depth and density of the liquid. So the hydrostatic pressure exerted on the gauge varies with the level of the water. As it turns out, every inch of water above the measurement point corresponds to a pressure of 0.0361 pounds per square inch, or psi. Every foot of water corresponds to a pressure of 0.433 psi. Now, in order for a fluid to flow in a system, certain pressure conditions must exist. This fact can be illustrated using this U-shaped tube that contains a liquid. Both ends of the tube are open, so atmospheric pressure is applied equally to the surface of the liquid in each leg of the tube. Since the pressure is the same in both legs, there's no flow, and the level in each leg is the same. But if additional pressure is applied to one leg of the tube, the liquid in that leg is forced downward, while the liquid in the other leg rises. In other words, the liquid flows because of the difference in pressure that's applied to the two legs. A fluid system is made up of components that function together to perform a specific task. To accomplish its task, a system must have at least 4 basic parts to satisfy certain key requirements. For example, a system must have an energy source to provide the energy necessary to carry out the task, a transmission path to transport the energy or process medium from one place to another, one or more control devices to adjust or change operating conditions in the system, and one or more components that carry out the specific task of the system, and in doing so, create a demand or load on the system. While the basic requirements of a fluid system can be divided into these 4 categories, the components that help satisfy those requirements often fall into more than one category. For example, a control device may also be considered part of the transmission path. To get a better understanding of how a fluid system is structured, let's look at how the requirements of a liquid system are met. In a liquid system, the energy that's needed to perform a task is often supplied by a pump. A pump adds energy to the liquid and creates flow. 2 types of pumps commonly found in liquid systems are positive displacement pumps and centrifugal pumps. While these pumps operate differently, they both cause flow by creating a pressure difference in the system. Generally, if a pump in a liquid system is not operating, there's no pressure difference in the system, so there's no flow. But when the pump is started up, pressure changes will occur. When the pump is started up, the pressure at the inlet or suction of the pump decreases, while the pressure at the outlet or discharge of the pump increases. As a result, liquid is drawn into the low pressure area at the suction of the pump, then discharged at a higher pressure from the outlet of the pump, causing flow through the system. While pumps commonly serve as the energy source for liquid systems, other components can share that responsibility. For example, a heat exchanger may function as an energy source if it adds heat or thermal energy to a liquid. But regardless of the component that's used, the basic requirement is the same. The system must have an energy source. Another basic requirement of a fluid system is to have a transmission path to move fluid from one place to another. In a liquid system, the transmission path is made up of components that the liquid flows through, such as pipes, valves, and tanks. Control devices are also needed by a fluid system. They're basically mechanisms that adjust or change the operating conditions of the system. Control devices for a liquid system typically include control valves that start, stop, or regulate flow, as well as instruments that monitor and control operating conditions. Adjusting control valve settings is a common way to control the flow rate in a system equipped with centrifugal pumps. But besides changing flow, these adjustments may also affect other variables in the system. Adjusting control valve settings to change flow will also affect pressure, since flow and pressure are so closely related. The way that the discharge pressure of a pump varies with flow can be illustrated using this graph. On the graph, the horizontal axis represents flow rate. Here, the flow rate is given as a percentage of the pump's capacity, but it's often represented in gallons per minute. The vertical axis of the graph represents the discharge pressure. If the pump is running and the control valve is fully closed, the discharge pressure is at its maximum value for the pump's speed, while the flow rate is 0. As the valve opens, the flow rate increases and the discharge pressure decreases. When the valve is fully open, the flow rate is at its maximum value, while the discharge pressure is at its minimum value. The curve that's formed on the graph is sometimes called a pump characteristic curve. Basically, it provides a way to see how a pump's discharge pressure is affected by different flow conditions. The fourth basic requirement of a fluid system involves carrying out the specific task of the system, and in the process, creating a demand or load on the system. In a liquid system, the components that fulfill the load requirement are often heat transfer devices. For example, this condenser carries out the specific task of a cooling water system. It removes heat from a vapor in another system. Inside the condenser, heat is transferred from the hot vapor to the cooling water that flows through tubes inside the condenser. The condensation process causes the vapor to change into a liquid. If the flow rate or the temperature of the vapor increases, more heat has to be removed from it. Under these circumstances, the cooling water system must be able to supply more water to absorb more heat, so the load on the system increases. If the flow rate or the temperature of the vapor decreases, less heat has to be removed, so the cooling water system doesn't need to supply as much water. In this case, the load on the cooling water system decreases. In a plant system, energy is converted from one form to another so that the system can perform its task. An important principle that's associated with the conversion of energy in a system is the law of energy conservation. The law of energy conservation states that energy can neither be created nor destroyed, only altered in form. This means that all of the energy in a system can be accounted for. The total energy that's present at any given point in a fluid system consists of different forms of energy, including thermal energy, which is energy related to the amount of heat in the fluid; kinetic energy, the energy related to the motion of the fluid; potential energy, the energy related to the position or elevation of the fluid; and what we'll call flow energy, the energy related to the pressures associated with fluid flow. Based on the law of energy conservation, as long as no energy enters or leaves a system, any change in the amount of one form of energy at a given point in the system will result in a change in one or more of the other forms of energy. Let's see how this works. This illustration represents a section of liquid system piping with a restriction in it. Two pressure gauges are mounted on the piping, one just upstream from the restriction and one directly in the restriction. Once flow is established in the system, the flow and pressures settle out to steady state conditions. In other words, conditions in the system remain constant over a period of time. Under these conditions, the pressure indicated by the gauge mounted in the restriction is less than the pressure being indicated by the upstream gauge. This difference in pressure occurs because at the restriction, the flow area is smaller. Now, we said that the energy related to the motion of a fluid is kinetic energy, and that the energy related to the pressures associated with fluid flow is flow energy. With that in mind, we can say that the energy conversion that's taking place at this restriction is a conversion of flow energy to kinetic energy. In other words, the liquid's pressure decreased, but its velocity increased. In the example we just looked at, flow energy was converted to kinetic energy, but at other sections of a liquid system, different types of energy conversions take place. For example, here's a section of piping in which two pressure gauges are situated at different elevations. The flow area of the pipe at the two gauges is the same, but the pressures being indicated by the gauges are different. In this section of piping, the decrease in pressure results from an increase in elevation. As we said earlier, the energy related to the position or elevation of a fluid is potential energy, and the energy related to the pressures on the fluid is flow energy. So the energy conversion that's taking place in this section of piping is a conversion of flow energy to potential energy. In general, energy conversions that occur within a liquid system have no effect on the total amount of energy in the liquid. But energy sometimes enters or leaves a system as well, and these energy transfers, as they're called, do affect the total amount of energy in the liquid. One device in which energy transfers commonly take place is a cooler. The purpose of this particular cooler is to transfer heat from a hot process liquid to cooling water. The hot process liquid enters the cooler here, flows through what is known as the shell side of the cooler, and exits here. At the same time, the cooling water enters here, flows through the tubes in the cooler, and exits here. As the process liquid makes contact with the cool tube surfaces, heat is transferred from the liquid through the tubes to the cooling water. The thermal energy that's transferred out of the process liquid causes the total energy in the process liquid to decrease. And since the same amount of thermal energy goes into the cooling water, the total energy in the cooling water increases. Energy transfers and energy conversions occur continuously in fluid systems. Sometimes these energy conversions are enormous. For that reason, there are some precautions associated with fluid system operation. For example, it's important that flow control valves in a liquid system be properly adjusted to prevent changing flow through the system too rapidly. The energy conversion from a rapid flow change can create a pressure pulse that travels through the entire system. When the pulse encounters bends or restrictions in the piping, it slams into them, causing a shock to the system known as water hammer. In severe cases, water hammer can cause piping to rupture, or it can damage other system components. By following operating procedures, you'll stand a better chance of avoiding these types of problems. In this topic, we examined some general information about plant systems and fluids, and we described the basic structure of a liquid system. We also described energy conversions that occur in a liquid system. Now let's try some practice questions. In a plant, many different pieces of equipment work together to perform one or more jobs. Any group of connected components that function together to carry out a specific task can be referred to as a plant system. Control devices are also needed by a fluid system. They're basically mechanisms that adjust or change the operating conditions of the system. Control devices for a liquid system typically include control valves that start, stop, or regulate flow, as well as instruments that monitor and control operating conditions. When a constant flow of liquid passes through this narrowed section of pipe, the pressure of the liquid decreases and the velocity of the liquid increases. Different types of gas and vapor systems can be found in process facilities. Although these systems may look different and serve different purposes, they each have to have at least 4 basic parts to satisfy certain key requirements. For example, a gas or vapor system has to have an energy source to provide the energy necessary for the system to perform its task. a transmission path to transport the gas or vapor from one place to another, control devices to adjust or change operating conditions in the system, and components to carry out the specific task of the system, and in doing so, create a demand or load on the system. The basic structure of a gas or vapor system can be illustrated using a compressed air system. In a compressed air system, the energy source is normally an air compressor. The air compressor adds energy to the system in the form of increased pressure. The transmission path for the system is made up of all of the components that contain the compressed air, including the piping and hoses that connect the components in the system, as well as a tank called a receiver that stores pressurized air for systems and equipment. Control devices which adjust or change operating conditions in the system typically include valves and regulators that help control the flow and pressure of the compressed air. Instruments that monitor variables in the system are also examples of control devices. The compressed air system also has components that use the compressed air to carry out the system's function. As they do, they create a demand or load on the system. In this system, these components include air-driven or pneumatic actuators and pneumatic tools. Now try a question about the structure of a compressed air system. This actuator is part of a compressed air system. It uses air to position a valve that controls the flow of liquid in a pipe. Which basic part of the compressed air system is the actuator's operation associated with? Many of the gas and vapor systems in process plants have similar features. For example, many of them have pressurized storage tanks or pressurized cylinders to store the gas. Also, gas and vapor systems commonly use valves to control the flow of gases from the containers. Another component that's used in liquid as well as gas and vapor systems is a jet pump. A jet pump uses the flow of one fluid to move another fluid. An air ejector that uses steam to remove air and other non-condensable gases from a condenser is one type of jet pump. There are no moving parts inside a jet pump. Instead, the pump relies on energy conversions to operate. The jet pump shown here has a nozzle, a pump inlet, a combining chamber, and a discharge section. During operation, high-pressure steam flows into the nozzle inlet of the jet pump and passes through a restriction in the nozzle. This causes a low-pressure area to form just past the nozzle. The low pressure draws the gas being pumped in through the pump inlet and into the combining chamber where it combines with the steam. The mixture then flows out of the jet pump through the discharge section. So in a jet pump, flow energy, that is energy that's related to pressure, is converted to kinetic energy in the nozzle, and the decrease in pressure that results from this conversion is used to pump the other fluid. Now, another device found in some gas and vapor systems is a condenser. Its purpose is to convert a vapor into a liquid by transferring energy. Inside a condenser, the vapor comes in contact with cool surfaces. In most condensers, the cool surfaces are tubes through which cooling water flows. Heat transfer takes place between the hot vapor that comes in contact with the tubes and the water that's flowing through the tubes. As a result, heat transfers out of the vapor, causing the vapor to condense to a liquid. As the vapor condenses, its volume decreases, creating a low pressure area. The drop in pressure draws more vapor into the condenser and enables the process to continue. Now, even though the low pressure inside a condenser is necessary for it to operate, it can also lead to some undesirable conditions. For example, there's always a chance that air will be drawn in through leaks or with the vapor flow. Air won't condense, and if it's allowed to build up, it can eventually fill the condenser and stop the flow of vapor. If this occurs, the condenser is said to be air-bound. To prevent this problem from occurring, air removal systems, such as an air ejector, are normally connected to a condenser. A similar problem can occur if the condensed liquid isn't removed. As with air, if the liquid is allowed to build up, it can eventually block the flow of vapor. In this topic, we described the basic structure of one type of gas and vapor system, and we examined the operation of various gas and vapor system devices. Now let's try some practice questions. The basic structure of a gas or vapor system can be illustrated using a compressed air system. In a compressed air system, the energy source is normally an air compressor. The air compressor adds energy to the system in the form of increased pressure. Another component that's used in liquid as well as gas and vapor systems is a jet pump. A jet pump uses the flow of one fluid to move another fluid. An air ejector that uses steam to remove air and other non-condensable gases from a condenser is one type of jet pump. There are no moving parts inside a jet pump. Instead, the pump relies on energy conversions to operate.